Any questions? Yes, you have a question? Your hand was not raised. You videotaped. Okay, I was trying to duplicate. So there was a question asked before you started about going over the fundamental domain. So, good question. Let's go over the meaning of the fundamental domain. So, I had said that the fundamental domain for this is the unit circle. This is e to the okay. So this is e to the 2 pi I over 6. This is e to the 2 pi I over 3. Minus a half to a half. So this is height root 3 over 2. So this is the fundamental domain for SL2Z. And I had said also that if you take this region, so this goes infinitely far up, if you take this region and you flip it over using the matrix S, where T is 1, 1, 0, 1, with the effect of tau goes to tau plus 1, and S is 0, minus 1, 1, 0, it's tau goes to minus 1 over tau, so outside the unit circle goes inside the unit circle, well, Euclidean unit semicircle. And so infinity goes to 0, and these points get flipped, and in any case, this whole region comes to this whole region, and then one more region, and this was this ST on F. So you translate this over 1, and then you flip it, and the reciprocation and negation, things over here get inside the circle on the left side. And so I said this is a fundamental domain for the group denoted gamma 0 of 2, which are the matrices A, B, C, D in SL2Z that have lower left entry common to 0 mod 2. Okay, so actually as a group, it's generated 0, minus 1, 1, 0, 1, 1, 0, 1, 1, 2, 0, 1. I'm not saying that's obvious. And kind of in the same way, you can show this is generated by 0, minus 1, 1, 0, and 1, 1, 0, 1. One can work out generators of these things. So what's the meaning? The question was, what does it mean when I say this is a fundamental domain for this group, or this is a fundamental domain for this group? Well, let's take a look more simply at the integers on the real line. The integers act by translation. And what's a fundamental domain for the action of adding integers to real numbers? The term fundamental domain means kind of a nice set that contains representatives from all the orbits of the group. So I want to find a bunch of real numbers so that up to addition by an integer, everything can land in that set. The natural thing to use is the interval from 0 to 1. Okay, so interval from 0 to 1 is a standard fundamental domain. Every integer can be added, every real number, you can add a suitable integer to it to land in here. There's a little bit of a problem on the endpoints. Both 0 and 1 are in the same orbit. Otherwise, every real number has a unique orbit element in here except at the endpoints. And so the meaning when I say this is a fundamental domain for SL2Z is that every point in the upper half plane for some gamma in SL2Z is transformed into a point in there. This point might have a different gamma than another point. I'm not saying the same gamma will move everything in. That's not what happens. Look over here. It's not like you add the same integer and move everything into here. Each real number has its own integer that puts you in here. Some real numbers, if you can move to 0, you can also move to 1, but otherwise there's a unique way to go in. On the boundary, there's a little bit of a duplication, and same thing here. If a point can be moved in here into the inside, there's only one way to do it. If you try to move a point into here and you wind up on the boundary, you wind up over here, you can also add 1 and it'll still stay in there. Here, you apply S and stay in there. So there's a little bit of duplication on the boundary. So everything in SL2Z transports the whole space into here. Now, if you take a subgroup of SL2Z, this is a subgroup of index 3, so you have 3 sets here. This is a smaller group. So if you have a point in the upper half plane, I can move a matrix. I can move it into here by a matrix in SL2Z, but maybe that matrix is not in gamma 0 of 2. And so when I say this is the fundamental domain, a subgroup has a bigger fundamental domain, the point is that the elements that transport you into here might not be in that subgroup. And so if using only that subgroup, the best you can do is you might land in here. You could have done it originally with that subgroup. But if you can't, then using this subgroup, you could land in here or here. Okay? And these 3 sets are related to this having index 3. And the same thing would happen if I took subgroup here of index 3. If I took adding multiples of 3 instead of adding integers, the standard fundamental domain would be, of course, the interval from 0 to 3. And you could think about it as a union of the original fundamental domain for the bigger group Z and 2 translates of it. Okay, sort of coset refs for Z mod 3Z. Same thing here. In some sense, these choices of F and what you translate by are related to using left coset representatives of this group. But this group is non-abelian, so sometimes you have to worry about something in the inverse or if it doesn't commute. But that's basically the idea of a fundamental domain, a nice space that contains the representatives from all the orbits. Right? Yeah. Question?
Yeah, so the fundamental domain of gamma 0 of 2 is the union of
Yes,
those 3?
yes,
Okay.
yes. It's all this stuff. It's 3 times bigger, just like the fundamental domain for 3Z is 3 times bigger.
Thank you.
Yes. Yeah. There's no guarantee, by the way, that if you work out things algebraically, that the fundamental domain you get is going to be 3 sets that are packaged next to each other. I could have used as a fundamental domain for 3Z, interval from 0 to 1, interval from 2 to 3, and interval from 4 to 5, or something. They don't have to all be next to each other. It would be nice. Maybe there's a theorem out there that would guarantee, under suitable situation, you can find a kind of a connected fundamental domain. But in any case, it's kind of the ideally you'd like to have a nice connected set. Other questions? So at the end of last class, we had 2 open issues. One was I was trying to convey the idea that you can have modular forms for subgroups that are not modular forms for the whole thing. And I gave the example of the modular form of weight 2 if you fiddle with it a bit. And so what I had said was, can we turn on the lights? Can someone go in the back and hit the lights?
There's also a
Wait. I have everything under control.
You want 1.
1. Let there be light. Okay. All right. So what we had last time was we introduced this holomorphic function in the upper half plane, and I had said that, well, it converges in the upper half plane, invariant after tau goes to tau plus 1, it's finite as tau goes to I infinity, but it doesn't satisfy the transformation law for weight 2 that you might think intuitively should have, because we just set k equal to 2 in the Q expansion of the honest Eisenstein series and just see what converges. It's an honest function, but I had said that it doesn't quite satisfy the weight 2 transformation law. I had written down that it's off by this amount. And I mentioned that there was a non-holomorphic function, essentially 1 over the imaginary part, which satisfies the same funky rule. And if you can scale it by, I think, 3 over pi, you can make this correction term match. Then the difference actually satisfies the weight 2 transformation law for tau to tau plus 1 and for minus 1 over tau. But that correction that cancels out this term is not holomorphic, so you have to write non-holomorphic modular forms. But an alternative, and I had mentioned this is what brought up modular forms for subgroups, was if you take 2e2 of E2 tau, and you subtract E2 of tau from it, this is another function that, in some sense, transforms like this with some funny correction factor, but when you subtract them, the correction factor disappears, and so this satisfies the weight 2 modularity condition, not for all of SL2Z. It does not transform in the way you would like for minus 1 over tau, but for all the matrices, I'll just write shorthand, the SL2Z matrices that look like something, something, 0, something, mod 2, these ones it transforms nicely under the weight 2 transformation law. And this is it's holomorphic in the upper half plane, and it's what I said, it's a modular form, so this is an example of a modular form of weight 2 for this subgroup. You can't have any modular form with weight 2 for the whole group SL2Z. I said that's the 0 space. You still have to compute those dimensions. I hope we do it today. But I defined what a modular form means, and I don't want to. We're not going to go through the detailed calculations. I'll write it up and add the lecture notes. But you're supposed to have these. It's holomorphic, and for this subgroup, it satisfies the modularity condition, and then the substitute for being bounded at infinity is being bounded in some sense, still for all of SL2Z, and sort of it's a more complicated looking condition than just being bounded at infinity, but we're going to kind of gloss over it for the purpose of talking about it here, but I just want to stress that being a modular form for a subgroup is not only take the modularity condition only for the subgroup and leave everything else alone. But that third condition, being bounded at infinity, it gets more complicated in some sense because you have to worry about not just behavior at infinity, but behavior everywhere in the fundamental domain that touches the boundary of the upper half plane. Infinity, or in this case, you have the point 0, so you have to study the behavior of the modular form near 0, and so there's kind of two conditions of boundedness, not quite that the function is bounded at infinity and at 0, but something related to that is going on. So the third condition involves these points, which because the shape of the fundamental domain has this funny corner or tip, these points are called cusps. And so we say the function used to be holomorphic at the cusps. But you can't see that here because infinity, we don't really have a picture for it. It's just out there. But here you can see these come together, so we can call those points the cusp. You get the cusp at infinity, and then we have the finite cusps that you can see here. They're all rational numbers. SL2Z on infinity will be a rational number. So any fundamental domain picture you see for a subgroup SL2Z and finite index will be a bunch of these funny triangular type curvy shaped regions, and they'll have a bunch of spikes touching the boundary. And you have to study the behavior of the modular form at those points and at infinity, and all of that behavior is the new third condition. But I'm just going to say, turns out this fits those conditions, and for this subgroup. So I want to use this to solve a classical problem about showing why every integer is a sum of four squares. Okay? And so I'm just going to kind of sketch the idea behind that. And so we're going to get this classical theorem of Lagrange. That every integer greater than or equal to 0 is a sum of four squares. I mean, this had been conjectured long before Lagrange. I believe Fermat, I think, had conjectured this. But Lagrange was the first one to prove it. And the proof was not constructive. He kind of showed that it could be done, but there was an improvement. Later, Jacobi, what year was this? 1834, actually went better than this and gave a formula for the number of ways to write an integer as a sum of 4 squares. The formula is manifestly positive, so it's kind of a quantitative improvement. So here's the formula for n greater than equal to 0. I'll write R4 of n for the number of ways of writing an integer as a sum of 4 squares. But when I write this, so the number of 4 tuples a, b, c, d in the integers that make a squared plus b squared plus c squared plus d squared equal to n. There's a lot of duplication. If you can do this once and you change the signs in a, b, c, d, you get new representations. So you might think this is kind of redundant, maybe I should only count positive. No, it's good to count all ways of doing it, even allowing negative a, b, c, or d. Well, the theorem is not the definition of the notation. The theorem is an actual formula, and here's the formula that he gave. Jacobi's formula. It has 2 versions depending on if n is odd or if n is even. And if n is odd, it's 8 times the sum of the divisors of n. That's the number of representations, okay, of an integer, the sum of 4 squares. And if n is even, the number of representations is 24 times the sum of the divisors, not of n, but of what I'll call n odd, the odd part of n. Just divide out the power of 2 in n, and what's left is called n odd. And so that's what we get. For example, let's try n equals 1. I want to write 1 as a sum of 4 squares. Well, 3 of the terms are going to be 0, and one of them will be plus or minus 1. So it's 2, 4, 6, 8. It's 8 choices. And 8, sigma 1 of 1 is 8. It works. Okay. If n is even, you can try that for yourself and test it for n equals 2. 2 odd is just the number 1. It's a pure power of 2. So it's saying there should be 24 ways of writing 2. So you just have 1s and minus 1s and 2 zeros and all kinds of stuff. And so you can do the combinatorics and check that it matches the number 24. So Jacobi proved this, and he had a method of using infinite series, but he wasn't using modular forms. He was using series. I think he wrote the letter Q. He introduced the letter Q into all this stuff, eventually developed into modular forms. So I want to explain how this formula can be derived using spaces of modular forms. So I don't know who actually was the first to realize that this can be done directly using modular forms. Or maybe the modular form proof that I'm going to sketch is an elaboration of Jacobi's arguments. So here's the idea. So to count the number of ways of writing a number as a sum of 4 squares, I want to introduce a generating function. So these are called theta functions, and so I will write theta of tau, the sum m greater than 0, e to the 2 pi I n squared tau. All right? Okay? Fine? All right. So here tau is a point in the upper half plane. And so what does this look like? So if we let q be e to the 2 pi I tau, it's summing q to the m squared. And yeah, so I guess if n is 0, we get 1. And then if n is 1, or do I want to sum over? No. I want to sum over all integers. So one thing you learn when you do these kind of sums of square representation counts is it's much more convenient to sum over all integers rather than the positive or non-negative integers, because summing over all integers you have the ability to use things like Poisson summation, right? Summing over all integers or more generally over a lattice, so summing over a group, not a semi-group or whatever the integer. What's the positive? Is that a monoid? I can't never remember. Magma? I don't know. So if you sum over all integers, m equals 0 is 1, but then you get 2q to the 4, 2q to the 9, and so on. So don't confuse the q's with the 9s. They're clearly different from each other. So this is a very boring power series. But, you see, if you raise it to a power, say you raise it to the 4, why not? Let's just get right to the point. You're going to be multiplying this thing by itself, and so when you multiply everything out and the dust settles, of course here you only have squared exponents. But when you start multiplying them 4 at a time, you're going to have a bunch of different q to different squares added together, and so you're going to get every exponent will be a positive number, and the number of times a q to the n will show up will be exactly counted by the number of ways you can write n as the sum of 4 squares of integers, possibly negative integers being squared. Yeah, does it make sense? See where this is coming from? Okay. Raise this to the 4th power, and you get this generating function. And it's not clear at this point why do I want to think about it as a function of a complex variable? Why don't I just take the formal power series in an indeterminate cube, and then just take the 4th power? Why do I need to pull it back to think about it as a function on the upper half plane? So maybe Jacobi was just working directly with these things. The point is, a modular form, you can't tell that something is a modular form just because it's a power series. A Q expansion encodes the tau to tau plus 1, but the tau to minus 1 over tau stuff is very hard to express, to see in the power series. So we pull it back to make it a function of a complex variable, and then it turns out, fact, based on Poisson summations, maybe I'll just write that here, one can show that the 4th power of this guy is a modular form of weight 2 for the group gamma 0 of 4. So these are the matrices in SL2Z, whose lower left entry is divisible by 4, and the other stuff can be whatever you want. Of course, being whatever you want, it can't be random, because it's supposed to have determinant 1, and that's even, and these had better both be odd, for example. So it's not like you have complete freedom, but determinant 1 integer matrices with the lower left hand multiple of 4. It turns out that this 4th power is a weight 2 modular form for that group, and this one, theta itself, in some sense, is a modular form of weight 1/2. Remember when you multiply modular forms, the weights add to weight 1/2, 4th power becomes weight 2. Okay? But odd modular forms of a half integer weight, very complicated. Weight 1/2, weight 3 has much more subtle than the integer weight stuff we've been talking about. In any case, raised to the 4th power becomes an orthodox ordinary modular form of weight 2 on this subgroup. And the subgroup gamma, so this is gamma 0 of 4. Now how is gamma 0 of 2 related to gamma 0 of 4? One of them is inside the other. Which one? The top is inside the bottom, or the bottom is inside the top? Yeah, right, it's divisible by 4, so we have that containment. And so a modular form for gamma 0 of 2, the thing that transforms nicely under this group, well, it's inside of here, so it should also be a modular form for gamma 0 of 4. Okay? So this example that I gave before, that was weight 2 for gamma 0 of 2, turns out that the space of those is only 1-dimensional. But on this smaller group, it becomes, this is 2-dimensional, and this guy that I wrote down before is in here, and there's another one that's in here. So it turns out, so this guy is in here, which is also in here. And, let me try, I don't miswrite things here. Here's another example. 2e2 of 4 tau minus e2 of 2 tau. So essentially, it's this guy where you replace tau with 2 tau everywhere. You just double the tau in the modular form, which means in the Q expansion, you're sort of replacing Q with Q squared. Double the tau everywhere. So this is also in this space. Not in the smaller space. This is 1-dimensional, but this has turned out to be 2-dimensional, and these are two functions that are in there. And let me show you what their Q expansions are. Are there any questions?
Did you swap the 2 for thirds?
So,
Oh,
no, because the smaller set of matrices that you have to make.
if you're modular,
means there's
if you're,
more possible modular.
yeah, if you're, it's sort of like, remember with the fundamental domain, if you have a subgroup, it has a bigger fundamental domain. How did that happen? Well, you need more. If you're modular for this group, then you're modular for the subgroup. This is a one-dimensional subspace of this. Yeah. Yeah, sometimes you have to stop waiting. Is that really right? So we know the definition of the Q expansion of E2 of tau. So to get E2 of 2 tau, you just double the taus, and you get signal 1 of n is showing up where 2n appears. Anyway, so you can work out, so let's give these names. What do you want to call this one? Call this one F1. Call this one F2. Thank you for your volunteering. So it turns out, here are the Q expansions of these. So the Q expansion of this guy, where was it? F1 is 1 plus 24, summing over 1, summing over n, sigma 1 n odd q to the n. Okay? It is a plus 24, not a minus 24. You do have a difference here. Anyway, you just work this out. Here are the first two terms, 1 plus 24q, dot, dot, dot. And the second one, because tau is always showing up in the context of 2 tau, the Q expansion will have all even powers of Q. And I worked this out, and it is 1 plus, oh yeah, I said before, it's just replacing tau with 2 tau, so in Q notation, I'm just replacing Q with Q squared. And so in fact, it starts off with 1, but the next non-zero term, the 24q squared, the linear part, is 0. And so you can see immediately that these are not scalar multiples of each other. They have the same first coefficient, but they don't have the same linear coefficient, for example. And if you trust me, please do, this is a two-dimensional space, well, then here's the basis. But wait, I said that this was a third example, theta to the fourth, and, well, this by definition has its own Q expansion. And what does it look like? It starts off with a 1. That's when n equals 0. I can write 0 as the sum of 4 squares. And the linear coefficient, you don't need Jacobi's formula. Just like, what's the linear coefficient? How many ways can you write 1 as the sum of 4 squares? We already went over it. Plus or minus 1 squared, 0, 0, 0. So it's plus 8q plus dot, dot, dot. So if you use this as a basis for this space, if you believe that it really is two-dimensional, well, this has to be a linear combination of these two guys. If you use that basis, then that means that the sum of 4 squares generating function is some number times the first plus some number times the second, and so it becomes a linear algebra problem. You need a plus b. Look at the constants. You need a plus b to be 1, and you need 24a to be 8. So what's a? 1/3. So a is 1/3. And I already said that they add up to 1, so b is 2/3. And so now I will leave it to you to check that if you take, for each integer n, and if you're very careful, here we'll only have even numbers, but for each integer, we'll call it m, that the 1/3 of the coefficient of q to the m here plus 2/3 of the coefficient of q to the m here exactly reproduces these two formulas. And so this is a modular form approach to deriving Jacobi's formula, and notice that the only thing I needed was to know how to write 0 and 1 as a sum of 4 squares in all possible ways. Those two numbers got me the coefficients, and then everything propagates. I get my linear relation everywhere, And so it's part of the beauty of modular forms. You get the first few things to match, and then they have to be equal because it's a finite dimensional space. You have to know the dimension and point of basis. And then they have to be equal all the way up. So we can predict, from knowing these two values, we can predict the value everywhere else. We can derive the Jacobi formula in this way. Okay? And it's sort of nice that we have an exact formula. And once people found this, they said, well, what about sum of 8 square representations? They could find an exact formula for that. But eventually, if you look at sum of square representations for other numbers of squares, you start to lose the ability to get exact formulas. You get a main term and then an error term. And if it's an odd number of squares, like writing integers as sums of 3 squares or 5 squares is much more complicated. Turns out to be related to modular forms of weight, of weight 3 over 2, and much more complicated than modular forms of integral weight. But it's just kind of a sketch of an idea. Surely one has to, of course, figure out how would you prove that this is if you could prove this is two-dimensional, and then you have to prove that, well, all 3 of these lie in there, then it just becomes a linear algebra problem. Okay? So there is the task of how do you actually compute the dimensions of these spaces, and then find out that proof functions are actually in there. So I will illustrate the dimension calculation by working out now the dimension formula for the space of modular forms of each weight for the group SL2Z. Okay? So we want to work out the dimension formula for that. We'll write out what the formula is. Remind you, we saw it last time. And then we'll discuss how you would prove such formulas. So if I'll write m sub k for the modular forms of weight k for SL2Z, so the set of all of these is a complex vector space, and so we wanted to compute the dimension. So we want to show it's 0 if k is negative. Let me say we want to show for, how about let's just say for even k. We already know it's 0 if k is odd. So for even k, we'll show 0 if k is less than 0. And then if k is 0, 4, 6, 8, and 10, we want to show it's one-dimensional. If k is 2, it's back to being 0-dimensional. And then for k bigger than 12, I want to show that it's the dimension of mk minus 6 plus 1. So, so you get a kind of recursive formula. And the thing I wrote down last time was the greatest integer of k over 12, or the greatest integer of k over 12 plus 1. This was if k was 2 mod 12, and this was if k was not 2